안녕하십니까. Many thanks for inviting me to this conference. I'm Young-Suk Seo, R&D Center Director of WONTECH Medical Laser Manufacturer. Today's my talk, Development of Picosecond Alexandrite Laser for Treatment of Skin Aging. Why use Alexandrite lasers? As with all medical lasers, it is common to use proven lasers that have been used in the industrial fields for medical applications. However, interestingly, Alexandrite laser has very little demand in the industrial field. So why is dermatology only demanding Alexandrite lasers? This is the answer to the fundamental question of developing a picosecond Alexandrite laser. As the most important application area of Alexandrite lasers in dermatology. Such lasers are used for skin rejuvenation, for removing tattoos, and for treating scar and pigmented lesion. This is an optical properties of Alexandrite laser crystal. Alexandrite lasers are chromium-doped solid-state lasers based on the crystalline gain medium, which is chromium-doped barium aluminum oxide. They are natural Alexandrite gemstones, but material for laser crystals is artificially produced and grown in monocrystalline form with high crystal quality, using a modified surface growth method. Emission wavelengths are typically between 700 to 800 nanometer, in many cases around 755 nanometer, where the maximum laser gain can be achieved. Alexandrite is highly anisotropic, having a low symmetry. As a consequence of that, the absorption and gain properties strongly depend on the direction of the polarization of light. This, together with the strong birefringence of the material, makes it easy to obtain linearly polarized emission with low depolarization losses. Here is an important point of Alexandrite laser crystals property. Alexandrite rod can not only tolerate elevated temperatures, but may even work better there. The spectroscopic properties of Alexandrite are substantially more complicated than those of Nd:YAG, not only due to the directional dependence, but also because of the strong involvement of phonons in the lower laser level. An unusual phenomenon is that the achievable laser gain and efficiency are highest not at lower temperatures, but at elevated temperatures. First, the Alexandrite lasers often work better with the elevated temperatures of the laser crystal. You have to consideration of picosecond laser pulse generation. In order to realize picosecond laser pulse, at least three technologies are required to be combined. And the laser having a narrow pulse width with high power energy has been developed by applying pulse generation technologies such as Q-switching, mode rocking, and cavity dumping. Q-switching can implement high power but has limitations with nanosecond pulse scale. But mode rocking can be made to produce pulses of light of extremely short duration. But mode rock technique is not easy to obtain high power energy. We have developed laser cavity is consists of large Poker star, polarizer, high refractive coating mirror, and off coupler. We designed cavity using a QC and cavity dumping technique. This is a part of picosecond laser system. QC and picosecond pulse generation is required electric and electronic control technology with microsecond and nanosecond scale. To generate picosecond laser with high power energy, an ultra high speed and high voltage driver is commonly used. So we have to merge different technologies of optical technique, electric and electronic control technique. This is a signal chart of laser pulses. QC is started at processor 1. After T1 delay, high voltage is applied to processor 2. After passing twice through processor 2, the polarization is rotated by 90 degrees. T2 pulse applies a narrower pulse than TR. TR minus T2 amplified in the injection pulse resonator, dumping at build-up time that maximizes. For example, cavity length of 0.5 meter can be obtained 0.9 nanosecond output pulse width. This is a time interval count design. The feedback control algorithm and circuit are designed for stable pulse and real-time output stabilization. We need to accuracy with nanoscale and resolution with picoscale. You can see the specification of the developed picosecond Alexandrite laser system. We have achieved 10 Hz frequency recently. You are sorry too late. As you know, that this laser system needs sufficient temperature in a laser cavity. So we needed to wait startup time and we need to wait down the temperature before plug up the system. This is a beam profile and pulse width. We can see the uniform energy distribution of the beam profile, allows safe and effective treatment results to be predicted. And the pulse width displayed on oscilloscope measure data using photodiode with 30 picosecond rising time. We have provided two types smart handpieces. Zoom handpiece can be collimated at 8 mm up to 50 cm away, and the micro-lensed array handpiece have a all spot size in one handpiece. As you can see absorption spectra, the absorption by melanin versus hemoglobin at 755 nanometer displays preference for 755 nanometer over 532 nanometer and 1064 nanometer. When considering the epidermal absorption of three wavelengths, you can see not only the effect of absorption of the first chromophore and melanin, but also the effect of the lower absorption coefficient of the secondary chromophore hemoglobin in the blood vessels. According to the Emil's paper, As you can see the table, when examined, the absorption of melanin relative to blood is the greatest for 755 nanometer. For the considered three wavelengths, melanin and blood absorption, you can see that the greatest blood temperature occurs with 532 nanometer, right followed by 1064 nanometer, with the least occurring at 755 nanometer. Values colored green are the most advantageous for avoidance of side effects in a clinical treatment. Thanks to all who love OneTech. We look forward to meeting you with good products. Thank you for attention.